Hi! Bobby Shafto posted a really nice challenge recently. There is this video of the moon, along with the date of the recording here in the description, and the challenge is to figure out the observer's latitude. If you know a bit about the movements of the objects in the sky, you probably know that this can be done based on the angle between the path of the moon and the horizon. So let's try this approach. So first we need to figure out which hemisphere this is on. If I play the video, the moon appears to set from the left to the right. It moves slightly to the right. So that would point towards the northern hemisphere. But if you look closely, something isn't quite right. Look at the surface features of the moon. The moon's northern pole, which is here, it's to the left, and southern pole is to the right. That's the orientation at moonrise, not moonset. This is actually moonrise played backwards. And taking that into account, this had to be recorded on the southern hemisphere, as the moon rises to the left. Note that Bobby even warned us to be careful, because there is a small detail that might be important. This was it. So having that out of the way, let's measure the angle between the path of the moon and the horizon. I took two screenshots, one from the beginning of the video, and one more towards the end. Now when we overlay them, by just reducing the opacity of one of them, we can easily measure the angle of the path. We can just take the measure tool, choose a point, let's say, on the top of the upper limb, and measure to the top of the upper limb here. So now GIMP shows us that this is 58.14 degrees. Now on the equator, the moon would rise straight up at 90 degrees to the horizon. Everywhere else it will be angled. As a first approximation, we can take the difference between the angle and 90 degrees to be the latitude. So 58 degrees would result in the latitude of 32 degrees. 90 minus 58 is 32. But there is a catch. This only works if the moon is directly over the equator. If it isn't, the angles are different. To see why that is, let's look at this drawing. Imagine the observer as standing in the middle of the celestial sphere on the horizontal plane. And flat earthers, hold your horses, this doesn't mean that the earth is flat and there is a dome. We're just using a convenient model here. So the sky is rotating around the celestial poles, and the angle between the line connecting the poles and the horizontal plane is equal to the latitude. We'll label it alpha. So now let's take a look. If a celestial object is above the equator, it follows this path and the angle at the horizon is equal to 90 minus alpha. But let's take a look at another object. This one barely touches the horizon and the angle is very small. Objects close enough to the poles even don't touch the horizon at all, so there is no angle to speak of. Clearly, if the moon isn't above the equator in the video, we need to take that into account. We can check where the moon was because we have the date. And as it turns out, its declination on the 24th of July 2021 was about minus 23 degrees. That's quite far from the equator, so we need to do some math. Let's start by drawing the plane of the celestial equator. This plane is perpendicular to the line connecting the poles. Now let's draw the daily path of an object with a declination delta. This will be a circle parallel to the plane of the equator, with the angle between an equatorial radius and radius to that circle being equal to delta. What we're interested in is this angle beta and how it depends on alpha and delta. We can also think of this angle as an angle between two vectors, v1 and v2. v1 will be a vector within the horizontal plane, tangent to the celestial sphere, and v2 will be a vector within the plane of the object, also tangent to the celestial sphere. Let's also introduce some Cartesian coordinates. Let the horizontal plane be the xy plane, with x pointing towards one of the poles, and z be vertical. Now, let's try to express the plane of the object's path in an equation. The general equation of a plane is constant times x plus constant times y plus constant times z equals constant, where the first three constants form a vector perpendicular to the plane. Here I labeled it u. And the last constant defines how much the plane is shifted from the origin along that vector. We can figure out the constant a0 by considering the equation for a point that belongs to the plane, for example the yellow point here. If we assume the radius of the celestial sphere to be 1, which we can do because the dimensions don't matter here, and if they mattered we could use units in which the radius is 1 anyway, So if we assume that, then the distance of the yellow point from the origin is just sine of delta. Now, this distance is along the line connecting the poles, which is at an angle alpha to the x-axis, which means the coordinates of the point are sine delta times cosine of alpha, 0, and sine delta times sine of alpha. The vector u points along the axis, so if we assume its length to be 1, which is generally useful and we will see later why, then the coordinates will be just cosine alpha, 0, sine alpha. Now we can substitute the coordinates of the vector u and the point into the equation, and we get this. We can simplify it a bit, and we get that a0 is just equal to sine of delta. Let's now try to figure out the vectors v1 and v2. We'll start by calculating the coordinates of the point of intersection between the horizontal plane and the plane of the path of the object. This point lies in plane A and has the z coordinate equal to 0. So we get x times cosine alpha plus 0 equals sine of delta, which means that x is just sine of delta divided by cosine of alpha. We can calculate y from the knowledge that the point lies on a unit circle, so its distance from the origin is 1. Then x squared plus y squared equals 1, and so y equals square root of 1 minus x squared, which equals square root of blah blah blah. Now that we know the coordinates of the point, we can figure out the vector v1. To do that, let's focus on the circle within the horizontal plane. v1 is a vector tangent to that circle. The coordinates of the red point, on the other hand, are equal to the coordinates of the vector from the origin to that point. Let's denote that vector by w. Now to figure out the coordinates of v1, let's look closely. Both v1 and w vectors are unit vectors, and v1 is perpendicular to w. This means that if we draw the segments along the axis here and here, we'll get identical triangles, because this is a right angle, so this angle here is equal to 90 minus this angle here, and this angle plus this angle plus this angle must be 180 degrees, which means this one is 180 minus 90 minus this one, so it's equal to this one, and this is again a right angle, and this one has to be equal to this one. Let's label it with 2 arcs. So those are not just similar triangles because they have all the same angles, but they are identical because the length of this side, the length of the hypotenuse, is the same in both cases. So this means that the x-coordinate of v1, which is this, is equal to the y-coordinate of w, only with a reversed sign, because here we go in the negative direction and here we go in the positive direction. And y-coordinate of v1 is equal to the x-coordinate of w, this time without the sign reversal. Okay, so we got this expression for v1. Now that we have v1, let's try calculating v2. To do that, we'll note 3 facts. First, v2 is in the a-plane, which means it is perpendicular to u. This can be written using the dot product, as the dot product of u and v2 being 0. Similarly, w is perpendicular to v2, as it is along the radius of the sphere, and v2 is tangent to the sphere. Finally, we'll want v2 to be a unit vector, like the 2 other vectors. I'm writing this using the dot product, but it just means that the sum of the squares of its coordinates are 1. Now we have 3 equations for 3 unknowns, so we can start solving them. To make our lives easier, let's denote the coordinates of v2 using x, y, and z. This can be a bit confusing because so far I used the letters to just denote the coordinates of arbitrary points, but let's just remember that from now on they mean the coordinates of v2. Since this is the last thing that we'll be calculating, we won't be using these letters in other meanings again. So the 3 equations written using the coordinates look the way you can see on the screen. Let's now copy this to an empty screen and start solving. The second equation can be simplified by multiplying both sides by cosine of alpha. To satisfy the first equation, we can assume x and z to be equal to some constant eta times minus sine of alpha and cosine of alpha respectively. Eta will be what is often called a normalizing factor. We'll calculate it later. Substituting x to the second equation, we get this expression for y. Now we can substitute all of this into the third equation and solve for eta. This looks a bit intimidating, but actually a lot can be simplified here. Let's start by copying all of this to an empty screen again. Now dividing both sides by eta squared, we get this. The sum of sine squared and cosine squared of the same angle is always 1, so we can use that. And after bringing the terms to a common denominator, we get this expression. This can be simplified by extracting a common factor of sine squared of delta. Now again, 1 minus sine squared of alpha is just cosine squared of alpha because of the identity I mentioned a moment ago. We can extract a common factor again, and again use the identity to get this fairly simple expression. From this, we can write that eta equals square root of cosine squared of alpha minus sine squared of delta divided by cosine of alpha cosine of delta. Not too pretty, but could be worse. We can now substitute eta into expressions for the coordinates of v2 and we get this. So now that we have v1 and v2, we can calculate beta. Using the dot product, we can express cosine of beta as the dot product of v1 and v2. The expression would be slightly more complex if v1 and v2 weren't unit vectors, and this is exactly why I decided to make them unit vectors from the get-go. So let's substitute the expressions for the coordinates and we'll get this. Looks a bit complicated, but if we look closely, we have a common denominator in the fractions, and the first one has minus sine squared delta sine alpha, and the second one has plus sine squared delta sine alpha. So this simplifies right away to just sine alpha divided by cosine delta. And that's it. We have the expression for the angle beta now. So knowing the angle between the moon's path and the horizon, beta, and the moon's declination delta, we can calculate alpha by just multiplying cosine beta by cosine delta and taking the inverse sine. Okay, let's do just that in Python. First, let's import some mathematical libraries. Okay, so now the angle between the path and the horizon beta was 58.1 degrees. We'll have to convert that to radians because trigonometric functions in Python use radians. So that's radians 58.1. Now the declination delta was minus 23 degrees and 11 minutes, so I'll write it like this. Oh, and we actually need to convert it to radians as well. Okay, so now we have cosine beta times cosine delta. So that is the sine of the latitude, and we can do the degrees arc sine. This is the inverse sine of the result, and tada, this is the latitude that is calculated using this method. So this is actually how I got the result I initially submitted to Bobby, but then Bobby told me that I'm still a few degrees off, and I started thinking how I could get more precise. Then I figured it out, let's correct for refraction. Correcting for refraction would be easy if we just knew how much of it there was. As we know, atmospheric refraction lifts celestial objects up, so to speak. So we just have to lower the initial image of the moon by some amount, like this, let's say. If we knew by how many pixels to shift it, we just lower it. We could do the same to the final image of the moon as well, and then just measure the changed angle. But we don't know how much to lower the images, so can we work around that? Yes, we can actually. The only thing that affects the angle is the difference between how much the two images are lifted up. If we lowered them by the same amount, the angle wouldn't change. So what we really need to do is figure out just how much more is the lower image affected than the higher image. And this we can figure out from the moon itself. If we measure the horizontal diameter, it is 305 pixels. Now, if we measure the vertical diameter, it is only 268 pixels. This means that the lower image of the moon is lifted 37 pixels more than the upper image. And that happens over the space of 268 pixels in the apparent image, but that's the only thing we can measure. So now we need to look how much lower the second image of the moon is. The coordinates are 359 and 7 for the upper image, and 637 and 443 for the lower image. So the lower image is 436 pixels lower. This is 443 minus 7. So the correction for refraction will be that difference divided by 268 and multiplied by 37, and this is how many pixels we have to add to the vertical difference. So the vertical difference is again 443 minus 7, and we need to add this correction, and so this is now our vertical difference. Let's label it dy. So the horizontal difference, on the other hand, is the difference between the x-coordinates, so 637 minus 359, and that's it. So the angle beta, the angle of ascent, because this is a moonrise, will be arcus tangens, or inverse tangent, of dy divided by dx, and this is this many in radians, so let's save that as beta. And if you want to see degrees value, so degrees beta is 60.7, which is a bit more than 58.1 we measured directly. Now the declination delta is again radians, minus 23 minus 11 minutes, and we can calculate the latitude by doing the same calculation, cos beta times cos delta, and the latitude is inverse sine of this, and convert to degrees, and tada! So we got approximately 26.7 degrees south. Now Bobby actually told me, well, he told me after I posted my comment under his video, he told me that the video was taken from the Sunshine Coast in Queensland, Australia. So let's check what the latitude there is. It's slightly north of Brisbane here, and we check, and it's 26.66, so roughly 26.7. Looks like a really good match. Alright, so that's it. I hope the math wasn't too intimidating. In any case, this shows how powerful it is and how much you can do when having a working model. I'd love to see flat earthers calculate the latitude from the video, and correct in numbers for their perspective, optical drop and whatnot. I don't think it will ever happen though, and we all know why. So thanks for watching and see you in the next one.